Okay. Yeah, you just have, I usually don't hand stuff out. I don't use hand stuff out in the lecture because it takes forever. Walking through silly desks. You can always stop by my office. I'll turn them back during lab. But they're great. You can always, you're more than welcome to stop by my office anytime and pick them up. And if not, I'll hand them back tomorrow. So yeah, so. All right, I don't think we did this one. You want to analyze cadmium nitrate solution, Cadmium is gonna be a heavy metal. What mass does sodium hydroxide need to precipitate cadmium ions from 35 milliliters of 0.5 molar cadmium nitrate solution? Anybody need a periodic table? Need one, Vin? Yes. Anybody else need one? Makes sense. All right. Everybody remember what the big M stands for? It's molarity. Yep, this is molarity. And the units of that are going to be a mole. This can be a mole of sodium over liter solution. Okay, so that's going to be the definition of M. All right. And I'm the same way as you folks. A lot of times when I look at a problem, I wonder, how do I start a problem? You ever notice that? You ever struggle with that exact same problem? Man, how do I start a problem, right? Even today, even after doing this stuff for longer than I care to admit, a lot of times I look at problems, how do I start this? Certainly if my mind isn't thinking chemistry. I tend to teach some physics classes as well too. Or if I'm teaching a chemistry class and I'm going to ask a physics question, it's hard for me to shift real quick. Now, but on these problems, where do you start? If you're given a concentration and a volume of a substance, that's where you start. Okay, 100%. That's always where you start. If you're given a concentration and a volume, that's where you start. Okay. Now, first thing we're going to do is we're going to write a balanced equation. We have cadmium 2 nitrate, right? Cadmium 2 nitrate. Is cadmium nitrate going to be soluble? Yeah. Yes, absolutely. It has a nitrate. Anything with a nitrate is going to be soluble. And it's going to react with a hydroxide, so it's going to form a precipitate. Does that make sense? Because most precipitates are going to be insoluble. And it's going to react with sodium hydroxide, right? This is going to be a +2 charge. That's a -1, +1, -1, correct? And the cadmium is going to react with the hydroxide, and the sodium and the nitrate are going to remain in the aqueous solution. We're good? Any questions on that? We have 2 of those because this is going to be a +2, that's a -1, and that's going to be our precipitate. And +2 sodium nitrates. Any questions on that? Good. All right. What we want is we want to know how much of the sodium hydroxide is going to react with all the cadmium. Okay. And we're going to start with the cadmium nitrate, cadmium 2 nitrate, because we have both the volume as well as the concentration. And it doesn't matter if you want to start with the volume or start with concentration, it doesn't matter. What we're going to do here is we're going to go, when you give a molarity, we're going to go moles. Let's see, molarity to moles, and then at this point we can either go grams, sometimes you go grams, sometimes you go back to molarity.
Question.
Yeah.
Why did you put the 2 there?
To balance it out.
Shouldn't I be two?
There
Really?
should be a 2 right there too.
Okay.
Thanks. Yep. Yep, thanks. So we'll go to molarity, we're gonna start with molarity, go to moles, and the moles, and then either grams or molarity. Sometimes we can also go to molarity as well too. Alright. So we start this as 0.500 moles. And nitrate, 1 liter. Multiply this by the volume, 0.035 liters. Bless you. I just simply convert it into liters. Now we're in moles of cadmium 2 nitrate. And what we want to go to is moles of sodium hydroxide. Know for every 1 mole cadmium nitrate, we have 2 moles of sodium hydroxide. The moles of cadmium nitrate cancel out. And now we know that, so this comes now from the pure act table, we know for every 1 mole of sodium hydroxide, that's going to be 40 grams of sodium hydroxide. And our moles of sodium hydroxide cancel out. Makes sense? And so for this, I got 1.4 grams. Cadmium 2 plus is what will precipitate out. Good? Yeah,
To get the 0.035, that's you converting it from milliliters to liters?
yeah, I wanted the liters down here to cancel. You could do another step. I just moved that decimal point over 3 places, so I just do it in 4 steps. You can do it in 5 steps. It's whatever floats your boat. We're good? All right. This would just be a review of pHs. So the pH scale typically is, the equation for the pH scale is a measure of how strong an acid is, or it's really the concentration of H plus the hydronium cation in a solution. All right. So the definition of pH is going to be the minus log base 10 of concentration of the H plus. All right. Is everybody familiar with the log scale? Anybody not familiar with the log scale? So log scale is where you're basically counting by tens or orders of magnitude. Would you have a better way of saying it? If I have an acid whose pH is equal to, say 4, I have another acid whose pH is equal to 2. This is going to be more acidic. But do you know by how much? Is it twice as acidic? More acidic than that? Less acidic than that? This will actually be 100 times more acidic. It'll be 100 times more acidic. This would be 10 to the second. That would be 10 to the minus second. This would be 10 to the minus fourth. The actual range of the pH, we usually go from 0 to 14, but the actual range is going to be negative 1.1 to 15.3. So this is going to be extremely acidic. This would be very, very basic. So the smaller the number, the more acidic. The higher the number, the more basic it is. So the smaller the number, the more acidic. The larger the number, the more basic it is. We'll talk more about this in the second semester. But if we were to work for, say, Procter and Gamble, and we were making Crest toothpaste, I think they make Crest toothpaste. Anyway, if we were making toothpaste, we wouldn't be so worried about the pH, which would be for the acid. We'd be concerned with the PF, the minus log concentration of fluoride ion, because we would want to know the amount of fluoride that the manufacturer puts in the toothpaste. Does that make sense? If you're working for I had a student a number of years ago, she worked for a hot tub company. They installed hot tubs and tested the water in them. They're always worried about the PCl, the chloride concentration, which is kind of cool. This is the pH scale. Just some common substances. So your stomach juice, the acid inside your stomach is going to have a pH of 1. That's actually going to be 1 molar hydrochloric acid that's in your stomach. It's interesting though, when you vomit, that smell of vomit, that's actually what's called butyric acid. There's a way to turn that butyric acid, which is, I think, one of the most disgusting smells possible, into pineapple smell. You simply just add an alcohol to it in a very acidic environment. It's kind of cool. If you take organic chemistry, you'll do some of that stuff with Dr. Baldwin. It's called esterification. It's amazing. It's so cool. It's so amazing. You like orange juice? Orange juice is going to have a pH of 3.5. Tomatoes, anybody love tomatoes? Yeah, they were my daughter's favorite food until she discovered ice cream. Now ice cream's her favorite food. But tomatoes are going to be somewhat acidic. Any coffee drinkers? Yeah, liquor of the Christian world, right? It's kind of funny, right? If we have missionaries, we don't send them necessarily to share Christ. We send them to start coffee shops all over the world. Is what I've discovered, which I think is kind of sad, but it's all right. That's going to be pH of 5. My wife became a coffeeholic a few years ago. I blame her best friend for doing that because my wife never drank coffee ever. All of a sudden, she starts drinking coffee. So part of the crowd. Have I told you my story with coffee? I was in about your age. I think I was a sophomore in college. I used to deer hunt a lot. And it rained all morning. And at that time, we only hunted a weekend. We only had a weekend to hunt. That was it for deer. And it rained and I was wet through and through. And then after lunch, the temperature just plummeted. Just, oh my goodness, it was so cold. I couldn't stop shivering. This old deer hunter said, "Here, this will warm me up." So I took a drink of it, spit it out, and said, "I'll stay cold. Thank you very much." And that's the only time I ever tried coffee. It's terrible. It's horrible. Rainwater is slightly acidic. Any idea why? Say what?
Atmosphere.
What about the atmosphere? Close, yeah. Say what? Pollution, okay. Let's say we go back to Noah's time, right? The very first time it ever rained, right? Because before then, how did the plants get water? Bubbled up through the soil, you know that? It actually didn't rain. If you were to go back and measure the rainwater, the very first time it ever rained on Earth, it would be slightly acidic. Yeah.
Is it because of what it picks up from the soil?
No, close. Kind of like what Logan said. So you take dissolved gases. So those dissolved gases in water will reduce the pH of water. So for example, if you were to take this, we'll talk about this later. Well, let's say that we happen to have, I don't know, let's say we have carbon dioxide. Take carbon dioxide, react that with water. What we create is carbonic acid. Right, so all these dissolved gases in there. Let's say you get some NOxes, right? You take NO, right? You have NOxes in here. You react that with water. We have to play with some of the play with some of the stoichiometry. But you can get different types of acids anytime you dissolve a gas into water. That's then going to make the rainwater itself acidic. So Logan, you're right, it's the atmosphere, it's the gases in the atmosphere that do absorb into the water that make the rainwater itself slightly acidic. Because rainwater isn't just water. So to the pollution thing, back in 1960, when we were burning tremendous amounts of coal, and the coal we were burning wasn't really clean, had a lot of sulfur. The sulfur would react with oxygen, right, to produce sulfates or sulfites. Well, sulfites, sulfur dioxide, sulfur trioxide, whatever it is, would dissolve into the water, the rainwater, and it rained obviously onto the earth. And which way does our weather flow from? West to east, correct? So a lot of these coal burning plants in the west would come this way and bring tremendous amounts of acid rain, particularly on Wisconsin, Michigan, up into Ontario. It got so bad that there are lakes in Ontario that could no longer survive. Life could not be sustained in them. So, yeah, but even if you go back to Noah's time, rainwater was going to be ever so slightly acidic because of dissolved gases in it. Blood is going to be 7.4. What happens to you if the pH of your blood goes up to 7.5 or down to 7.3? You die. Just becomes very important, and certainly in the medical field, as to what prescriptions you are to be taking, so it doesn't affect the pH of your blood. And then seawater is going to be basic. It's supposed to be, and this is going to be because of dissolved metals in water, of what drive down or what increase the pH, make it more basic. We may talk about that in the second semester. That's a little bit complicated how that works. But what it does, actually, the metals actually strip off the hydrogen off the water, leaving an OH, which is going to be slightly basic. You don't have to memorize it. It's just kind of some interesting stuff I thought. It's pretty cool. All right. This is why I like studying chemistry. I enjoy studying chemistry, not because of stoichiometry and math and all that stuff. So I enjoy seeing how God's creation works at the molecular level. I think it's just absolutely fascinating. It's just so complicated, so difficult, but I find it so fascinating just how this stuff works. And so I find this really, really quite interesting. One time my wife took a biochemistry class. She thought she wanted to change careers, so she took a biochemistry class. And she talked about heme. I remember one night she's studying heme, and that's the iron protein and hemoglobin. She talked to me for an hour and a half, and it was the most amazing, just absolutely fun. I've never had biochemistry. Big molecules scare me, I guess. But it was absolutely the most amazing, fascinating thing, how that works and how that actually changes the instant a baby leaves the mother's womb. It's just absolutely fascinating how that works. Just the beauty of God's creation. So the pH scale, the actual calculation of this, P once again stands for the minus log. We're going to look at the pH of minus log, the concentration of the acid. This is another way to write the acid. We'll get into this in the second semester. We can also look at the POH, which would be the minus log of the OH concentration. If we're, as that former student of mine once was, if we're going to be working with hot tubs or swimming pools, that we're looking at, or heck, we could even be looking at an aquarium shop where we're looking at that seawater, how much salt water is in the aquarium. We would be looking at the PCl. And we'll get into this stuff later, but pH plus POH is equal to 14. Don't worry about this pKw. We're going to talk about that in the second semester. We'll spend a month talking about just this goofy little K next semester. And it really isn't, at that point, that's when we're finally going to start talking chemistry. And you may say, oh, what are we doing now? Well, we're really just doing silly stuff to do silly calculations. But once we start talking about this stuff, then we start talking about the chemistry. And then you'll see how complicated that is, because we'll just look at the acid-base chemistry. One more problem here. Sorry, dude. Yeah. I'll let you work on this one for a little bit. So a positive blood test for carbon monoxide poisoning is indicated by the reduction of palladium get palladium 2 to palladium metal. Here's palladium 2 going to palladium metal. It looks like it's balanced because we have a 2 there, so it's 2 chlorides, 1 carbon, 2 oxygens, 2 oxygens. Okay, so we're good. If 1.5 milliliters of 0.01 mole of palladium 2 chlorides mixed with 0.001 carbon monoxide, the carbon monoxide is the limiting reagent, the water is the limiting reagent, the palladium 2 chloride is the limiting reagent, the palladium chloride and the carbon monoxide are present in equal amounts, so there is no limiting reagent. Now, first thing I'm going to tell you is, whenever you look at these multiple choice questions, and you're going to get this at the end of the semester, you can always eliminate 1 or 2 of the possibilities. Do we know anything about the water? No, and the water in this case serves as just a solvent, right? So we can completely ignore B, right? We don't need to worry about B, right? So what we want to do is we want to go to how much palladium is going to be produced from this, all right? Good, that makes sense? So how many times do we have to do stoichiometry? Twice. Now, notice the one with carbon monoxide is gonna be really, really, really easy, right? And it's just another hint, we don't have to do that last step of going to moles, we can just go right, or that very last step of going to grams. We can just go directly right to moles and stop there, because that's all we want to care about. It's just simply the amount, all right? I'll give you a few minutes to work on that. Oh my goodness, I can't spell blood either, can I? Blue. I was always the first kid to sit down in a spelling bee in school, but the last kid to sit down in a math bee. Can't spell anything. Chopped out, you ready? We'll do the easy one for the carbon monoxide. Move this something. We'll do the easy one, we'll go 0.01. Oop, one more zero, isn't it? Yep. 0.1 moles carbon monoxide. I'm just gonna go to palladium. And for every mole of carbon monoxide, we have 1 mole of palladium. And that is gonna give us the exact same number. You could go to grams of palladium if you want, do one more step and go right to grams of palladium, but we can just go with moles and that's fine, it'll save us some time. Now we have the 1.5 milliliters of the 0.01 molar palladium. So 0.01 moles. And there's other ways of doing these problems. You don't have to do them this way. There's other ways. Zero, oops. 0.15 liters. So I just converted the 1.5 milliliters into liters. That now gets us into moles of palladium chloride for every, it's 1 to 1, isn't it? Yep. 1 mole palladium chloride is equivalent to 1 mole palladium. Oh, so God, what's that gonna be? That's 1.5 times 10 to the 2, 1, 2, 3, minus 5 moles of palladium. So which one's gonna create the least amount of palladium? Yeah, the palladium chloride. So what's gonna be our linking reagent? The palladium chloride, because it produces the least amount of palladium. That makes sense?
Mhm.
Yeah.
Yours with like the times 10 to the.
Fifth?
Yeah.
You just moved it, I just wrote scientific notation. Just moving it over, right? So if you carried out this calculation. Right, so it'd be 0.00, maybe 0.015. Says your own scientific notation. That's all I do. Laziness, that's all it is. I just do that each quickly. Counting zeros. We're good? Yeah. I don't know which one's going to produce the least amount of palladium. So I have two reactants, right? I have carbon monoxide and I have the palladium. I have quantities of both reactants. Does that make sense? So I don't know if it's gonna be the palladium that's gonna be the issue. Or I'm sorry, I don't know if it's gonna be the carbon monoxide, or if it's gonna be the palladium 2 chlorides. So since I have information of both reactants, I gotta do it twice. Because I don't know which one it is. So that's why I had to do it twice. Good? Does that make sense? Good questions. Good question. All right. So this is the end of the material that's gonna be on the exam on Friday. If you have any help, or if you need any help, let me know. I'll email you out Kayla's or Kyla's information. She's one of your tutors. Anybody seen her yet? Pretty helpful. Yeah, she is. Yeah, spectacular student. And Dante favors another tutor for you. Once again, spectacular students. Last year's class was amazing. I haven't had a class like that in years. Kayla wants to be a teacher for whatever reason. I don't know why, but I was kind of teased about that. Go ahead and use her. She's very smart, very good at explaining things. Like I said, I'll email you her information when class is done. So this starts the beginning of the information on the second exam. This is thermal chemistry. So this would be kind of basically baby thermodynamics. We'll really get into thermodynamics in the second semester. This first few minutes that I go over, first couple slides, just gonna be definitions. I don't ever ask you definitions on the exam, ever. I just go over those definitions so we're able to communicate. There was a physics professor, bless you, whose office was right across the hallway, and I really enjoyed talking to him, but one of the best pieces of information he ever gave me was anytime you learn a new science, it's similar to learning a new foreign language. Any of you ever learn a foreign language? Yeah. I tried. I failed miserably at it. That's a whole other story, but it's essentially, you're trying to, it's essentially a foreign language. What do these words mean? Does that make sense? So I do a lot of vocabulary, I do a lot of, I go over quite a bit of that, so we're able to communicate, but I don't ask you what they mean on an exam. Does that make sense? This is not a vocabulary class. So. And all this has tremendous amounts of math underneath, okay? Um. So a system, this is gonna be whatever you're interested in. And you get to define what that system is, but you wanna choose it wisely, all right? Because if you choose it poorly, then the math becomes difficult or the experiments become difficult. So you wanna be careful with that. The surroundings is everything but what the system is, all right? Now, in this class, in this chapter, all we're gonna look at is how heat flows. So everything, there's a class in here, it's NSC 200. They wrote all kinds of neat stuff about heat and temperature. And that's really what we're going to be talking about. Is chemical reactions either give off heat when they occur, or they absorb heat when they occur. All right. And so we have the surroundings, which is going to be everything else. Now, if you're an engineering major and you're thinking about that field, the surroundings are what you're going to be most likely interested in. Biology, it varies, it depends. Chemistry, we're always concerned about the system. We're always concerned about the system. So that's what our focus is going to be on, the system. Now, the universe is going to be everything. That includes the systems and the surroundings, right? So the universe is going to be the systems and the surroundings. Now, if you were to take a more in-depth course on thermodynamics, these surroundings would not be everything outside the system. It would be just that thing outside the system that's intimate to the system, is really how it works. All right. So far, so good. Hey, you look at the stars last night, or make it outside last night? The wife and I got out last night finally and looked at the stars. Oh my goodness, I could actually see the Milky Way. It was amazing. We got away from Concord, went out in the middle of nowhere. Oh my goodness, I hadn't seen the Milky Way in years. Actually, I take that back. I saw it once this summer. Absolutely absolutely love looking at stars. I have big balls of fire, but boy, they're amazing. So a closed system is going to be a system that exchanges that can exchange energy with the surroundings, but not matter. Now, that's just always, these definitions always seem kind of stupid to me. Does that make sense? Because let's get into something practical. So let's say we look at Sarah's orange juice container. We'll look at that. Now she's got the lid on it. We could tip it upside down. Matter cannot come in, matter cannot go out. It's stuck there. But if we leave that in this room for a while, it's eventually going to come to the exact same temperature of this room, meaning that energy can exchange, right? Now, let's say her orange juice was really, really, really warm. She drank some really warm orange juice. What would happen then is that the heat would leave that orange juice and go into the surroundings. Or let's say if the orange juice is really, really cold, what would happen then is that the heat from the surroundings will go into the orange juice. So heat always flows from something high temperature to something low temperature. All right. That's what we'll talk about that a little bit next semester. That's the second law of thermodynamics, the energy, the law of entropy. So that would be a closed system. All right. So energy can exchange with the surroundings. So if we look at that bottle of orange juice as the system and the surroundings, then energy can exchange between the system and the surroundings. And this will occur until we get to what's called thermal equilibrium, or the same temperature. That makes sense? Another system we can have is what's called an open system. So if we were to take that bottle of orange juice and open up the cap, then that would become an open system, meaning that matter and energy can go into and out of that system. All right. So that would be an open system. And an adiabatic system is gonna be where matter and energy are not exchanged between a system and a surrounding. So this would be, for example, a cooler, an insulated cooler, something that would be insulated, does not let heat go into or out of. For example, those, I think there are those expensive Yeti cups, those things. The only Yeti cup we have in our house, I found snorkeling one time. Found it bottom of the lake, cleaned it up. Bought a lid for next to nothing and works great because it's stainless steel lined on the inside, so the germs and bacteria can't grow because they can't grow on stainless steel. So clean it up a little bit, call it good. That would be an adiabatic system, about as good as an adiabatic system as you could possibly get. So that would be an adiabatic system, right? Any questions so far? All right. Now, state functions, are these gonna be functions that depend upon the state of the system, all right? So whether it's a solid, liquid, or a gas. Okay, so that basically the phase of the matter. Now, all this underlying all this, so for example, a state function, you would deal with that mathematically. So every time you see one of these definitions, what it really has underneath it is how you deal with the stuff mathematically. We are not going to get into that, which is too bad. But a state function of property depends only upon the state of the system. So the temperature of something is going to depend upon the state of the system, right? So if we look at thick water, for example, if that water is going to be a vapor at atmospheric pressure and room temperature, now the vapor itself will not be at room temperature, but if we have water vapor, that's more than likely going to be at a higher temperature. Likewise, the pressure will also be a state function. I should go back to this. If we had water as ice, then that would have that temperature be dependent upon the state of that system. Right? And so the pressure also determines the state of the system as well. So change in the state function depend only on the initial and final state, not the actual path. That kind of gets to a little bit of philosophy and how to look at how to think about thermodynamics. In that we only measure the initial state, we don't measure any final states, or we only measure the initial state and the final state. We don't measure what actually happens in between. That's sort of the way the experiment is done. And with this, we always measure a change. There's always going to be a change. So a change in temperature, change in heat. There's always going to be some kind of change when we look at thermodynamics. And it doesn't matter upon the path. It only matters on the initial state and the final state. Whatever happens in between, we don't care. I guess kind of a nice analogy I always think about this is if you're traveling home to see your family only matters the initial state and the final state so long as you get home. Doesn't really, they don't really matter necessarily in the path you take, just so long as you get home. Good, that makes sense. These are just some definitions. I remember the very first time I taught this course a long time ago. I think I spent an entire day trying to come up with a definition of energy. Right? We talk about energy all the time. How do you define that? I remember that. I remember I struggled for a day. Just how do I define the term energy? And the closest thing I could come up with is the capacity to do work. That's I think the closest way I can come up to defining energy. Somebody wants to ask me, how do I define enthalpy? Or I'm sorry, entropy, the disorder, psychological thermodynamics. I said, well, I define that as the same way I define energy, the capacity to do work, because it is a type of energy. So you have energy, which is going to be the capacity to do work. We're going to give this a symbol E, right? We also have this thing which is called the total energy. So this is going to be the total energy of the system. It's going to be everything that system has, all the energy that system possesses. That's going to be your energy, your total energy of the system. Okay. Work. Work is energy used to move a massive object against a force. All right, so if I were to have somebody sit in a chair and I was going to move that person in that chair a particular distance, I would do that by applying a particular force to that object, moving it a particular distance, and that would be the energy from that. So that would be the work, the amount of work to displace from somebody from one place to another, or move an object from one place to another. In order to do that, you have to apply a force to that object. And then heat is going to be the energy that causes the temperature of an object to increase, and this is really nothing more than the random motion of molecules. Now, heat and temperature are not the same thing. Temperature is going to be the average kinetic energy of the molecules that we're measuring. With thermodynamics, the difficult thing about this is all the definitions, they all have these particular meanings to them. Something else I just, let me see. The funny thing is, all this was developed, so you'll hear a lot about steam engines and that sort of stuff. All this was developed in the 1700s during kind of the beginning of the Industrial Revolution, for the making, basically steam engine objects to do work for us. In that case, it's more mechanical. Here, we're going to talk about it more in terms of chemical, right? Also gonna say, not remember what it was, but it's the word. Must not have been that important. And there are two types of energy. There's going to be potential energy, which is the energy of located based on position. And then there's going to be kinetic energy, which is going to be energy related to motion. So if I have this marker up here, this will have a tremendous amount of, this will have more potential energy than it does kinetic energy. It does not have any kinetic energy as it is right now, because it doesn't have any motion. The moment I let go of it, the potential energy is going to decrease and the kinetic energy is going to increase, right? And so energy is neither created nor destroyed, it simply just changes phases or forms. I can't remember, I was gonna say something about work, but I can't remember what it is. It'll come to me. This happens to be the equation for kinetic energy. We're not gonna do anything with that. But it happens to be 1/2 mass times velocity squared, where mass is going to be in units of kilograms, velocity is going to be in meters per second. If you happen to have me in physics next year or next couple years, we'll spend a lot of time on that equation. Oh my goodness, we use that equation so much. It's an incredible equation. The units for energy, what we're going to use mostly is going to be the joule. The reason we use the joule is because it's a kilogram meter squared per second squared, and it's a really nice unit to work with. Those of you who are HES majors or into nutrition, what unit of energy do you study there? The calorie. You'll use the calorie. The calorie is the energy required to raise 1 gram of water, so that would be 1 milliliter of water. 1 degree Celsius, and that degree Celsius is 14.5 degrees Celsius to 15.5 degrees Celsius. You'll want to know this, 1 calorie is equal to 4.184 joules. In some places, well, for example, here in America, if we look at the nutritional value or the nutritional panel on a piece of some type of food product, if we want to know how much energy is in that food product, it will be reported in units of calories. Danielle, what's it like? What's it reported at your home? It's in calories, it is. We're in Tanzania, it was actually in kilojoules. I went there with a bunch of nerdy scientists, and it was in kilojoules. Everything was in kilojoules. In that case, it actually was in the kilojoules. 1 food calorie, so this is going to be your 1 food calorie is equal to 1,000 calories. So the capital C is going to be food calories, or it's also kilocalories. is equal to 1,000 of these calories, and also lowercase c and the capital C. Or it's equal to 4,184 joules. Or it's equal to 4.184 kilojoules, or that's going to be 1 food calorie. Confusing? Yes, no. If you remember just this number right here, it all comes from that. We're good? Okay, now potential energy, this has to deal with position. All right, don't worry about this, we're not, but all it simply has to do is position. Electrostatic potential, we'll talk about that in physics. We're not gonna do that now. All right, enough about that. I used to go over that tremendously, but I never ask any questions about it. So it's work. I guess the one thing I want to say is, how do we think about potential energy and kinetic energy in terms of chemistry? Because everything here, it dealt with really more mechanical, the location of an object from Earth or its velocity. But how we deal with this in chemistry is we look at the potential energy in essence sort of as the reactants, right? So those reactants would be thought of in terms of the potential energy, and then the products would be then the kinetic energy. Right? And what we're going to look at and how we think about this is the energy of a substance is always going to be in its chemical bonds. So we'll look at breaking and forming new chemical bonds. All right. Now, if we look at potential energy, if we look at the work, for example, work is going to be equal to force times distance. That makes a lot of sense, right? If my daughter was to sit in that chair over there in the corner and I was to push her down the hallway, I would be doing work on her by simply applying a force to her and displacing her. When they were smaller, you would see my kids a lot of times racing up and down the hallways. They put each other in a chair and run up and down the hallways. And who knows, they probably still do that if they didn't grumble at them a little bit. But that doesn't make necessarily a whole lot of sense when we talk about molecules. So molecules, we can look at this in terms of gases, right? So we can look at the work as being equal to the minus the pressure of the gas times the change in volume of that gas, right? So down here, there's kind of an interesting picture. So what we have here is we have zinc reacting with hydrochloric acid. So if zinc reacts with hydrochloric acid, that's the reaction we have. So what kind of reaction is this? Acid-base, neutralization, metathesis, precipitation reaction, redox reaction, what kind of combustion reaction, what kind of reaction would this be?
Redox.
It's a redox, that's exactly right. Yep, it's a redox because we have a zinc, which is at 0, going to zinc 2+, so it becomes oxidized, right? And here we have the hydrogen, which is a +1, going to 0, and in this case, it's going to be reduced. So this is a redox reaction. Now, this hydrogen gas that gets produced from that, we put the zinc into the HCl solution. That's going to produce hydrogen gas. And what happens is it's going to move this piston, all right? Because it's going to change the volume. So the pressure in the system is going to be the same, but the volume changes. So the gas did work on the piston. Does that make sense? We can also look at batteries, right? Charged battery doing work. We'll talk about this the second semester when we get into electrochemistry. by it giving off heat. It can actually turn the fan, it simply, as it flows through a resistor, which in this case happens to be a fan. And thus, that turns the blaze, which is going to then turn the molecules, which is then going to eventually do work. But that would be electrical work. Still work will be distinguished as electrical. I guess the best way I can think of thermodynamics or to explain thermodynamics to you is what makes it similar is it's all just energy. That's all it is. It's just energy. But once you identify the type of energy it is, that's how you treat it mathematically, and that's how you think about it. Does that make any sense? Let's look at an analogy, right? Money is a great analogy to thermodynamics. What are the different types of money, forms of money we have in this country? So hard currency, right? Cash, right? Cash. What's another kind of currency, another type of money, form of money we have in this country?
Digital?
We could have digital, yeah, we could do Bitcoin, right? We have Bitcoin, right? I've not done that. I wish in 2008 I'd bought $1,000 of Bitcoin. It'd be worth about $1 million now. I thought about it. Remember the first time I heard, like, oh, I should invest in that. I don't mind investing. I bought a bunch of I bonds back then. They're doing really well. Digital. What else? Are your vehicles worth money? So that's what's called equity, right? Any other forms of equity we have in this country? Houses, property, right? What else do you have? Precious metals, right? Stocks, bonds, right? All those are different forms of money. Does that make sense? Would I mow the lawn of my savings account? Would I wash my savings account? Doesn't make any sense, right? Would I wash my vehicle, right? So depending on type of money you have, you treat it differently. Does that make sense? Right? Same thing with energy. It's the exact same thing with energy. Do you have work? Or do you have potential energy? Do you have kinetic energy? Based on the type of energy you have, once you get that identified, that is how you're going to treat that. That makes sense? So that's kind of the analogy, I guess, to thermodynamics that makes the most sense to me. Is I look at the different forms of money I have in my household. How do I treat them? The exact same thing here. What type of form of energy do I have? The form that I have, that's how I'm going to treat it. That makes sense? Whether it's an open system or a closed system, or it's an adiabatic system, right? Based on that, that is how you ultimately treat those different forms of energy. Good? All right. We'll talk about the first law of thermodynamics on Wednesday. Then you have an exam on Friday, right? So if you have any questions, I mean it, just come up and ask for help, stop and talk to me. You are always welcome. Yeah.
Are you still gonna be in on Wednesday?
Yeah, I'll still be on Wednesday. Yeah, I don't go, yeah. Is it Serve Day on Wednesday?
Yeah.
Oh. You have Serve Day on Wednesday?
Yeah.
Well, anyway. I'll be here on Wednesday. I don't think we have class anyway. Okay, we don't have class. All right.